Okay, guys. In this section, we have both type of ICMP messages: the error and the query message. Now, as we discussed in the last slide, that the type will have 8 bytes total of the header, that is 32-bit, 32-bit. The first 4 bytes will be common. That is, the first 8-bit is type, next 8-bit is code, and 16 is checksum. Okay. Now, checksum you already know what is. The type and the code basically tells us what exactly the problem is, okay, in case of the error reporting. While in case of the query message, these are actually set by us because we are querying a particular type of thing. For example, if I'm dealing with something related to time, I will have my type as 2, and based on the code I want the data. For example, how much time do you average need to process a particular data packet? That is 1. For how much time or how much number of packets actually have time more than a particular threshold, that is number 2. Or how much actually have lost their TTL on your particular node, that is number 3. So inside a particular category, how much different things you have. Okay, for example here, 08 and 00 basically are echo request and reply. Now if you remember in the first option that we said, the first option was tell me what exactly is happening with a particular router. Okay, whether a router is alive or not, because let's say I'm having a lot of people going to this router, and since it's not active, it's taking alternative path. So a lot of path changes are happening around this router. So I just wanted to check whether this router is working or not. So I have sent a echo message here, and if it replies back, it means it's alive, else it's dead. Okay, it's not taking any more access. There is something wrong with the router physically, and for that you actually have to send someone to the actual router and fix that particular problem. But we get to know of such problems from a particular distance. Similarly, if I need a particular timestamp from that location, that okay, tell me when did you get this message and when did you send the message back. Let's say it says that I send the message back at 9:32 and I get it at 9:34. I can tell that okay, it takes 2 minutes from message to go from there to here. Okay, so those sort of query messages can actually be identified based on the type and the code. And in that particular set, I need the identifier and the sequence number for a very simple reason. Let's say that my host is doing a schedule check of all the routers in its proximity. Okay, it will send all of them the same double zero and 08, this particular message, to check whether all of them is alive or not. This particular thing is the same. The identifier will actually help me to understand. Identifier and the sequence number will actually help me to understand that which of the router I'm dealing with and which message sequence I'm dealing with. For example, let's say I have sent two things, the echo and the request for some sort of information. So this will actually have, this will be identifier A, this will be B, and this will be message sequence 1, this will be message sequence 2. Okay, when I get the reply, identifier for both of them will be same because I'm dealing with the same particular router. So it will be A1 and A2. So based on that particular thing, I can get to know that for what particular thing you are giving me the reply. Okay, for which particular message. If I have multiple messages transacting with you, the sequence number is just increased by +1 for that particular message respond. Okay, and the identifier is basically identify to whom have I sent the message. Okay, whereas in case of the error reporting, and if you actually see this particular thing, in case of query messages, I have sent something and I get something back. That is why I have a sequence number. This is A and this is A+1. The reason for that is very simple. I need to have to know what exactly the response is coming and whom is it coming from. Okay, so for that particular thing, the query messages are always sent in pairs. That is something that actually differs it from an error message, because error message are only sent from the router or the destination when something goes wrong. Okay, the header, the host doesn't actually send some sort of a message to get an error reporting message in response. This is a one-way message, and this actually has a pair. Okay, now the first 2 bits again based on what error has actually happened, we deal with those. Checksum is the same checksum. Rest of the header actually hold initial data. Okay, the initial data of the packet which has made the error. Okay, that is just to verify that okay, the whatever data section here tells me that okay, this is the packet I have identified based on the data which I have got, that this is the message which had the error. I will match the first 4 bytes with this particular 4 bytes to make sure that this is the packet I am dealing with. Okay, so this particular information here tells me what packet has missed it, and this is just for verification of that. Okay, Now, in the next slide, we will actually discuss about how do we reduce such messages, because if you actually see, we may have, let's say, 1,000 routers in a particular network. At the same time, we are sending, let's say, 10k messages per minute. Okay. Now, even if, let's say, 2% of the messages actually failed and we need to check the router every 10 or 15 seconds, I will have way too many ICMP messages for the host to work around with. So for that particular reason, we need to make strict rules when exactly can you use the ICMP message. For example, for no such random events, you can use the 911 call, right? So the same thing actually happens with here. You have certain restrictions when you can actually use the ICMP messages. Okay, so there is no ICMP message for ICMP response. That particular thing means to say that, let's say this is the host and there is a particular router and a packet P has actually failed. If I send a response, let's say ICMP 1, and that particular packet is just telling that the packet P has actually fell or has been lost around this particular router, and if this particular message itself is missing, I cannot send back another message saying that, okay, error message has already failed. Okay, so the error message will not actually get an ICMP, only the packet, and that too only once. Okay, now, what happens if the ICMP message, definitely it doesn't that easily go off, but if that particular message is missing or goes wrong some way, then this particular packet will be found missing by the destination, and the destination will send back the message to the host saying that I haven't got this particular packet. Okay, so we don't actually have ICMP for a ICMP response message. Okay, similarly, ICMP message will not be sent for any fragment. Okay, so if a particular data is divided into 3 sections, that particular section, if this is lost, I will not actually send any of the ICMP messages. Okay, but if I actually have, let's say, even in this particular section, or this is actually the first message, so let's say that message 111, if you remember the fragmentation video, 2 2 and 3 3 3. So my first message is divided into 1 2 3, and that 1 is divided into 3, the 2 is divided into 2 more parts, and 3 is divided into 3 more parts. All of these losses will not actually make any ICMP message go, but this particular, the very first message, if this message is somehow broken, then we will actually see that, okay, at this particular point I have to send an ICMP message. Reason is, if the first packet reaches the destination, any other packet, if it is missing, it will definitely send back an ICMP, because any of the packet which is missing between that, the offset value will actually tell me that the packet is missing. If the last packet is missing, then I will not have the m equals to 1 bit. Okay, m equals to 0 bit in any of the packets. So I know that at least one packet is going wrong. So in both these scenarios, I'm not sending an ICMP message, because the destination will be able to identify that it has missed a particular message. Okay, so the error reporting will actually happen from the destination part, and we don't have to take care of that. Okay, this is just reducing the overall load on number of ICMP messages that we have to send. At the same logic, there is no error message sent when we have a multicast addressing. Now, multicast addressing, if you don't know, it is basically when, let's say, the host H has sent multiple messages to destination 1, destination 2, destination 3, and all of them. Okay, so let's say a particular message which was sent to all of them, that message has been failed at some router X, RX. Okay, we cannot send back ICMP message for this, for one reason. This packet, I don't know which of the destinations are going to get, because we are using a data gram protocol, the IP. I don't know whether this packet was going to 1, 2, 3, 4, 5. So how, what would I tell? That send a message again to which one? Okay, it cannot send the entire message again, because it has to go to, let's say, 100 different destinations. Okay, so what I will do is that I will wait for the destination to tell me that, okay, I haven't received any message from you about whatever thing that you had to discuss, and because of that, it will send an error. It will send a message that, okay, I haven't got this particular message. Okay, or we can set up a response system that, okay, I have sent a message to D1, D2, D3, all D100, and I have received a response of R1, R2, R3 except R84. So I know that destination 84 was the one which actually lost that particular message, which I never got an ICMP fee for. But since D84 has not responded, I will send again a message. Okay. In case of multicast message also, I cannot know which message, whichever message has been lost, which of the multiple destinations was it assigned to. Okay, so even in that particular case, in all these three cases, the destination gets to know, or the host somehow get to know directly by the destination, or in this particular case, all the other destinations which got the message replies with an acknowledgement. The one which doesn't, we have to send the message again for those destinations only. Okay, the last one is when we have an ICMP message, is the no ICMP message is actually sent for reserved messages. Now, reserved messages are for particular IPs like 127.000 or all four O's. And the reason for that is that these are usually assigned to home or local system. Okay, so these are usually just to check it up that, okay, I'm sending some sort of a log or some sort of status to these messages. And if you haven't actually you have actually missed any of those, doesn't matter, the logs are sent every particular time interval, 10 second, 5 second, you send it again. Or if it has been way too long, those will actually come back to you because they are local systems. Okay, so in all these scenarios the messages are not sent. Okay, any of the scenario other than these, then only ICMP messages will be sent. Okay, so basically when I'm having a host, it is sending a one message to destination, let's say D1, and that message has been lost. In that particular scenario, I will get an ICMP message. Okay, so I've reduced all the possibility into some simple ones in which ICMP will report the errors. Now, if you actually think a little bit harder on this, you can see there are loopholes in here. Okay, there are a lot of better alternatives that you can actually come up with. For example, in the multicasting system, you can actually have a better system than all the other destinations sending us back. So we can actually have a simple ICMP message, but then again, you cannot trace that particular thing. So what you will do, you will add destination address with all of the ICMP. Right now, if you see in the last message, we don't have a destination in, we have the destination encapsulated in all of these, but the ICMP doesn't carry the destination. So in the higher versions, what we do is that we also copy the destination in which the message was actually going, so that we can understand or at least guess what particular messages were missing out of that. So the ICMP message which we are discussing here is called as ICMP v4. There is a version which has upgraded, and that is actually not a separate, but it has actually combined some of the properties with IPv6, and we'll discuss those when we reach to IPv6. Okay, but I hope in this particular section you understood why or when we don't need ICMP messages, because the error will be something which will be way too obvious and the host will get to know it even without an error reporting system. Right now, what are different types of error other than packet going suddenly whoosh? What are the other types of error? Okay, the most common one is a destination unreachable. For example, when you actually call a particular number that doesn't exist. Okay, now in that particular part you have actually sent some message to a number, but that IP doesn't exist. So in that particular scenario you will get an error. Okay, other than that, some of the very common ones, that particular one is pretty obvious, so I mentioned it directly. But other than that, one of the common ones is that when a package is dropped due to congestion. Congestion basically happens is if, let's say, multiple packets are trying to get in the same path. Let's say this is the destination and multiple packets are trying to go in the same path. Okay, for those who have actually studied the bucket flow system or the congestion protocols, congestion reduction protocol. Okay, the leaky bucket protocols. Okay, there are some sort of losses that actually happens in these. So if your packet has actually been one of those which cannot be actually holded in the buffer, let's say I have only buffer for 5 messages and the message which I have got is the 6th one, so I will anyway have to drop that message. If this message is dropped, I will get an ICMP for that particular situation. Okay, and the type will be mentioned as type 4. Okay, so based on that I can actually think that, okay, there's way too much congestion because of which my packet couldn't be delivered. So the best option is either to wait if you can. If you cannot wait, try another path to reach to the particular destination. Okay, other than that, redirection method. To understand this, if you remember in the past videos we have discussed in the options. Okay, in the IP addresses, an option in which you can actually give a particular set of path to the packet to reach a particular destination from the host. Remember, now if one of these, let's say there is some sort of a blockage or congestion or this particular router has died, then it will actually take an alternative path from here and then here. Now what happens is that sometimes these routers add certain values or they have some other response than just sending it through. If that particular scenario is there, we need the host to know that, okay, wait, there has been a change in the suggested path. So if the router redirects the package, a type 5 ICMP has to be sent to the host, so that the host know that the path has actually changed from from which it has actually suggested. Okay, so in future, if it sends another path in another packet in this particular path, it can modify the path initially itself. Okay, so those sort of errors, or those sort of modification, I wouldn't really call it an error, but those sort of modifications are actually in type 5. Similarly, if a particular TTL has actually ran out, we will send a type 11 message. Okay, the type 11 message will basically tell that, okay, the TTL has run out, you need to provide more TTL if you are sending another packet in this particular path. So that is something you can do in response of a TTL or type 11 ICMP error. Similarly, parameter problem. This very rarely happens because almost all the systems are nowadays automated. But let's say because of some sort of an error, whether it's a human error, mechanical error, or some sort of mistake in the protocol itself, you actually get one of the header values wrong. It doesn't make sense for the router, or the router, let's say, is not updated, or they're using different software, or some sort of error happens between them. The router is not able to understand the header of the particular message. Then it will send a type 12 error with the detail in the payload section. It will add the detail that, okay, this particular point makes no sense to me, and it will give a detail about that this is the error and this is what I'm not getting. Okay, so based on that, the host can actually see that, okay, this is something that this router may not know, so you can convert it in that particular type, or you can update the router software, or you can take an alternative path. Okay, so that is all the options you have for parameter problems. Now, query messages are usually only of two types. The first one is echo. Okay, echo request and echo reply. As if you remember in the last slide, we discussed that query messages will actually go in a pair. The host will actually send something to the destination, and then the destination will reply back to the host. So this is your type 8. Okay, and this is your type 9. And mostly the echoes are usually for route tracing and ping, which we'll discuss in the next slide. uh, Either to know whether the router is alive or not, or whether to know the path from this host to this destination. And now this destination can be a router or some other server. Now, usually the two purposes are ping and routing. That's covered. Similarly, to know time delay. Yeah. So what actually happens is that sometimes we need to know the time it has taken in a particular to and fro motion, because it's not a simple normal path that you can actually trace the packet's speed, because you have a lot of other factors. Sometimes it's other traffic. Sometimes it's congestion. Sometimes the routers is not reachable. Sometimes it actually has to wait in the buffer. So all those times included, you actually send a timestamp request. In that, you send the time that it actually has, you have actually sent the message, and the destination sends two times. One, the timestamp in which it has received it, and the other timestamp in which it has sent the message. So based on this and this, you can measure, and when it reaches you, based on these four timestamps, you can realize that, okay, it took some, let's say, 8 seconds to go in this direction and 9 seconds to come back. So on an average, it takes 8.5 for a trip from one point to the other. Or usually we actually cover these things in RTT, which is round trip time, that is to and fro. So 8 plus 9, that is 17 seconds. Okay, so these sort of calculations usually happen using the timestamp request. uh, Again, when we have requested, it's type 13 ICMP, and when we have got and reply, it's type 14 ICMP. Okay, now some of the messages, since we are learning with IPv4 and ICMP v4, both the versions have been upgraded in IPv6. We have certain things which have been removed in a way. The first one is information request and reply. Nowadays those are actually covered in the ICMP because the payload can. Secondly, this particular protocol for ask address mask request and reply, this actually has been covered by DHRP, that is dynamic host resolution protocol. Similarly, router solicitation and advertisement has been covered by this again. Address resolution is basically when you don't actually have all the addresses around you. Nowadays we don't have that particular problem. For those who have already studied routers before, this is basically to update your router table. That is actually taken care of by dynamic host resolution protocol. Other than that, routers solicitation and advertisement is when you have multiple routers and they don't know each other. They actually send advertisements and they then confirm with each other that, okay, yeah, you are a router, I'm a router, let's connect, and each of us should have the data. I can reach to these particular other routers and you can reach to each of them. This is how we usually earlier used to build a particular network, let each of these devices connect themselves. Nowadays we have a better protocol for all of this. Again, DHRP. We will not actually study DHRP in this particular section. We will study it when we are studying IPv6. But in this particular section you can understand that these three, if you by chance hear of these or read these somewhere, are not anymore used with the upgraded systems that we have. Okay. Now the last part, debugging tools. If you remember, 2 slides back, here we have studied about ping and routing, the use of the echo messages. That is basically the two things that we use for debugging some of the networks. Now, when do we actually debug a network? When we are taking way too much time. Okay, so too much time is actually somewhere, sometime when you need to debug, or you don't know the route. Okay, so if you don't know the route to a particular location, you need to remember that particular thing. So when you actually have to trace these sort of things, or you need to make a network. Okay, so the host has been introduced to the network very first time. It has to make that network graph for itself. Okay, so in those particular scenarios we need these sort of debugging or management tools. The ping is again very simple. It's basically to check whether a router is alive or not. A simple echo message: are you alive? Yes, or that's it. Yes, there's no. uh, the sequence messages are actually, sequence values are actually used for this. I send a 0, you send back a 1. Later I will send a 1, you will send a 2, and so on. Okay, that is just to check whether the particular router is alive or not. Okay, other than that, if you add the timestamp feature, you can calculate the to and fro time. Based on that, you can actually calculate how much time it takes for a particular message to go from one router to the other. And nowadays a lot of people have actually been doing a lot of studies using machine learning to understand better paths. They actually take the value in which RTT increase or decrease over time. This is in days, day 1, day 2, day 3, and this is the total time, the RTT time taken. A lot of people have been optimizing based on at what particular time the RTT was way too low. What was happening then? When what are the two instances at which it was high? So what was happening in this date and time? This is what happening in this date and time. This is how you usually debug a particular network. Okay. Other than that, trace route is usually done in a way which is actually easy to explain here in the second video. Yeah. So in this particular slide, if you see the host, what it does is that it sends a packet with a TTL of 1. It let it go. This router, let's say there's another router, let's say it takes both these paths, 1 packet each, and as soon as it reaches here, TTL goes 0 and we get an ICMP error message back. Okay, so here we have voluntarily made an ICMP message come back to us, and that is the error message that okay, your TTL has ran out. But I know that okay, these two are routers which are at 1 hop away from this host. Again, now what I'll do, I will send it to TTL2. It will reach till all the routers which I can read by 2 steps. Similarly, I will send it with 3. I will reach to all the routers in which I can go by 3 hops and 4 hops and so on. Okay, so that particular way, what you can do is that if this is your host, you can make that okay, D1, D2, and D6 you can reach by 1 hop. From D1, one more hop can actually take you to D3 and D4 and D2. Okay, so this way you can actually generate the entire network if you are entering that network for the very first time. Okay, other than that, we have one small, if you can see here, it's tracer. Now this is nothing new, it's just the basic trace routing. Instead of ICMP, a lot of times people use just IPv messages, 4 or 6 to trace the same application. We just have to create that particular thing, whether you do it for round trip time or to learn the number of hops. Okay, from one router to the other, all these things, when you need to use these sort of packets, these sort of, for these sort of applications you need to use IPv6. That's called as tracer. Okay, so that's all that is there to learn about ICMP messages. In the next section we'll discuss about mobile IP, which is a very important topic from the perspective that most of the devices that we are going to use in the next 10 years are going to be IoT devices, or the devices which are actually portable. We are not going to have any more telephone or desktops or any of the stable devices. Most of the devices that we are going to use are to be very portable and that too very fast. So we'll actually deal with mobile IP in the next section. I hope you have enough questions in this particular sections. If you have any doubts, please do put down them on the comment section. Thank you.